All right. Well, most of the halogens dissolve in water, and actually, while dissolving, they react in water to give acidic solution. The equation is given right in front of you. And for any other halogen, what you're going to do is that you're gonna change the simple symbols, and the rest of the equation will stay as it is. For example, with bromine, the reaction is going to be exactly same, except wherever we have chlorine, we write bromine there. And the rest, all the numbers and the letters, the symbols remain the same. In a similar way, bromine mixture is known as bromine water. If this one is known as chlorine water, that is known as bromine water. If we have hydrochloric acid formed over here, we'll have hydrobromic acid formed over here. If we have hypochlorous acid formed over here, we would have hypobromous acid formed over there. You can do the similar with fluorine and iodine in terms of naming. Chlorine water acts as an oxidizing agent. This specific acid is an oxidizing agent. It has an extra oxygen that it can give away with. Now, it also acts as a bleach because colored substances lose their color when they are oxidized. So, it can react with colored substances and actually convert them into colorless. We call this a bleaching action. This reaction is specifically used as a chemical test for chlorine. So what do? We dissolve chlorine in water, we make some chlorine water solution, and we react it with something. If it bleaches it, the water is some chlorine water. And we can go for the same reaction for the gas. We're going to cover that part hopefully in chapter number 12. Moving on, damp litmus paper or universal indicator paper, when it is dipped or lowered into chlorine gas, it is bleached. First, it is converted into red, then it is bleached. The halogens become steadily less reactive as you go down the group. So the reactions of bromine and iodine are going to be less reactive as compared to chlorine. Chlorine is going to have the most reactive of reactions. Make sense?
Yes, sir.
Okay, so moving on. The fourth kind of reaction, displacement reactions. For displacement reactions, the rule is pretty simple. A halogen in its original form can replace another halogen from its salt solution if the first halogen is more reactive than the second one. Or we can safely say a more reactive halogen can displace a less reactive one from its salt solution. Since chlorine is more reactive than bromine, so chlorine displaces bromine, takes its position in the salt solution, and bromine is given out. The whole changes of color in this portion is actually what we require and what can be done as a test. Now, chlorine is a pale green gas. Now, when that pale green gas passes through a colorless solution, and I'm going to write aqueous and gas next to it, it forms again a colorless solution, but the colorless solution becomes slightly brown because of this bromine present, which shows some of an orange color. Since it's dilute, it doesn't exactly give the brown color. You have this reaction over here, right? So chlorine is going to do the same with iodine, since again, chlorine is more reactive than iodine, so chlorine is capable of displacing iodine from its salt solution. Again, the colors are brown or yellow-brown. So what do we have? We have different sets of reactions that we can actually discuss. So chlorine bleaches any color dyes easily. Bromine bleaches them slowly. Iodine bleaches them very slowly, proving iodine is far less reactive than chlorine. If I react them with a metal, chlorine actually reacts strongly to form a metal chloride. It means a salt, but this reaction needs heat to start. Iron also reacts steadily to form iron 3 bromide with bromine, but this reaction needs continuous heating. Iron reacts very slowly, even with continuous heating, and forms a little amount of iron 3 iodide. So as you can see, it needs heat to start. This one needs continuous heating. Even on continuous heating, this goes very slow. Proves that chlorine is more reactive than bromine, and bromine in turn is more reactive than iodine. So You would notice one more thing. Chlorine can displace bromine and iodine from their salt solutions. Bromine can only displace iodine because it is more reactive than iodine, but it cannot displace chlorine from its salt solution. So there is no reaction. Sometimes these kind of reactions are written in order to confuse students. Let's say if you have a reaction written like this, they mean can bromine displace chlorine? So you're simply supposed to write no reaction. Why? Bromine is less reactive than chlorine. Displacement will not occur. Does that make sense to you?
Yes, sir.
Good. If that does make sense to you, both of the times when you're going to see no reaction written next to the column of iodine for chlorine and bromine, you'd understand since iodine is the least reactive one, it cannot displace either chlorine or bromine from their salt solutions. Why? Because iodine is less reactive. Now, you would notice that their equations are pretty similar even when we change the symbols for chlorine, bromine, and iodine. The rest of the numbers and everything else remains the same. All of these equations usually form a yellow or a yellow-brown solution at the end. So this kind of color change from colorless solution is an easy observation to tell us that the reaction did proceed, that the more reactive metal was able to displace the less reactive one from its salt solution. All right, so let's move on. This completes third group, group number 7, halogens for us. To be honest, if I go back and I see halogens, let me tell you one small fact about halogens. The word halogen itself means salt forming. All right. So it literally means that halogens are the compounds that form salt. And to some extent, this is completely correct. We do understand when they react with metal, they form salt. So that's why halogens are known as halogens because most of the salts that are used in bigger amounts on the planet are made up of halogens. Moving on, next group, group 8, better call it group 0, noble gases. As the name suggests, every single element in this group is a gas. Why the word noble? Because they have their outermost shell filled or at least stable with 8 electrons. All of these gases are a part of Earth's atmosphere, and one man, William Ramsay, was involved in isolation of all of these elements in the group. Before him, they were not even a part of the periodic table. So he was awarded Nobel Prize for his contribution. Noble gases are present in Earth's atmosphere. Together, they make up 1% of the total. Argon is the most common noble gas. These gases are pretty unreactive. We also use the term inert gases for them, but it does not mean that they do not react at all. Some compounds of xenon and krypton have been found or made. Their name was changed to noble gases because of their least reactivity. Yeah, we have a few compounds with them. That doesn't mean they do not exactly react, but most of the time, with most of the components, they are unreactive. For example, the most common of stuff in chemistry is usually affected by either acids or alkalis or oxidizing agents or reducing agents. Noble gases are not affected by any of these, be it acids, alkalis, oxidizing, or reducing agents. So that's why we keep calling them unreactive inert, and hence the word noble. Now, what are you supposed to do from this part? Since they don't react, we don't have any reactions to show with noble gases. Their uses is actually something that you are supposed to memorize. So you are supposed to memorize the use of helium in airships and balloons because it is light and unreactive, argon in filling of light bulbs because it does not react with the filament even at high temperatures, neon in the form of neon lights or advertising lights. All right. Advertising lights is an electric discharge tube which consists little amount of a noble gas, and when electricity is passed through them, different noble gas give different colors. Neon gives us bright red color, hence some of the advertising signs are made up of neon. Overall, for all the noble gases, their melting and boiling points are extremely low. Helium has the lowest melting point of any element, and it cannot be solidified by cooling alone. Pressure is also needed. You are just going to memorize the uses of those compounds and this whole pink portion. For noble gases, their electron arrangements are stable. They do not react readily with any atoms, bond, or react chemically, since they have a stable arrangement of electrons, and all other elements on the periodic table actually try to achieve their stable configuration by the loss of electron or gain of electron or sharing of electron. This also completes for us the topic of noble gases. Moving on, trends across a period. Now, for a period, we do understand that atomic size decreases. We do understand the metals are usually converted into non-metals from moving from left to right. As you can see, all your metals are on your left and all the non-metals are on your extreme right of the periodic table. So most of the period-based properties are something that we have already studied. So I don't think this needs a complete explanation because I've already explained it before a couple of lessons earlier. Moving on, transition elements. Transition elements are actually the center part of the periodic table. We may call them transition elements, we may call them transition metals. Instead of going with them from here, I actually try to jump to page number 65, and I tend to go with this big portion, which discusses for us the general features or properties of all transition metals. Well, most of them are hard and strong. Most of them are solid in at room temperature, except mercury, which is a liquid. They have high density, they have high melting and boiling points, and two of their distinctive properties are number one, their compounds are colored. We can safely say the color in the word is due to transition elements. As you can see, so many colors in front of you. The transition elements show so many colors. For example, if I talk about human body, if I talk about you, Beta, your skin tone, the color of your hair, the color of your eyes are all actually coming because of the presence of a transition element. Not just that, I hope you already know that human blood is actually composed of different blood cells. The most populated one is red blood cells, and I hope you know that red blood cells are red due to the presence of a protein by the name hemoglobin. Now, hemoglobin is a big molecule. At the center of it, we have one atom of iron. And of course, no transition elements show colors. So their compounds are colored, and that's because the red color of hemoglobin, in turn, the red color of red blood cells, finally the red color of our blood. So the colors inside the human body are basically mostly coming from transition metals. Moving on, the last point, they often show more than one valency, variable oxidation state, variable valencies. And hence, due to this point, since they keep on changing, the word transition. Transition means change itself. For example, iron can form compounds which can be iron 2 ions, which means iron can lose 2 electrons, or iron 3 ions, which means it may also lose 3. That's the transition That's the more than one valency or variable oxidation part that we usually discuss. So for transition elements, you're gonna see many colors. For example, iron can show different colors. Iron 2 ions have actually a different appearance than the iron 3 ions. Uh, to finish it up all here, let me tell you, iron 2 ions are green or blackish green in color, while on the other hand, iron 3 ions are red brown. So yeah, they can show variable valency and they can show different colors at the same time. Well, these properties are distinctive. Remember, the top three properties are general features and go with all transition metals or elements. The bottom two distinctive properties are different for different elements. For example, you might have seen on the previous page that they can show many different colors. So the colors are different for different species or for different transition elements or for the same transition element for different states. All right.
Yes, sir.
So lastly, in the end, in order to wind up the 3.2 topic, we have a very small topic by the name of position of hydrogen in the periodic table list. Now, when you look at the periodic table, you find hydrogen on the top of the periodic table. Unfortunately, you won't be able to put it to a group since its position would be so random that you will be clearly be able to see that hydrogen doesn't belong to any group. So the question is why? Why is the position of hydrogen so unique? And why is hydrogen not belonging to any of the groups in our bifurcations? In order to prove the point, what we usually do is that we try to compare hydrogen with either group 7 or group 1. Since hydrogen can show mixed properties of each, so that's what we try to remember. All right. Let me tell you for every, my bad, just a second. So for every similarity in this case with any of the groups, I'm going to write the letter S. And for any dissimilarity, I'm going to write the letter D. Now, hydrogen may be in one aspect, if it's similar to group 1, it might be different from group 7. So in this entire table, what you're supposed to see is that what is the difference and similarities of hydrogen with different groups. Now, lithium and fluorine are just examples from this group. The examination questions, as the past papers show us, may not necessarily compare hydrogen with the same elements every time. They may compare it with sodium instead of lithium, potassium instead of lithium, fluorine instead of fluorine, or bromine instead of fluorine. So remember, these are just examples. What they are trying to mean, what they are trying to hint at from with the help of lithium is that it's group 1, and with the help of fluorine is that it's group 7. Let's start comparing them. When we're going to compare, as I said earlier, so I am going to mention the similarities and dissimilarities. So hydrogen is a gas and fluorine is also a gas. So there you go. You have a similarity of hydrogen and fluorine, but lithium is solid at room temperature. So that's the difference you have. So moving on, if we talk about the metallic character, hydrogen is a non-metal, and I'm going to separate this point from the rest. So it's similar to fluorine, but it's dissimilar to group 1 metal. Now, hydrogen can form diatomic molecules, which is a pretty similar behavior to halogens, since all halogens form diatomic molecules. I hope you remember that all the halogens form molecules that consist of two atoms, hence the letter 2 beneath iodine in all these cases.
Yes, sir.
Let me clarify that metallic character and formation of diatomic molecules are two separate points and can always be written separately. Now, let's compare the number of valence shell electrons. You're going to get astonished that this time the similarity of hydrogen lies with group 1 and difference with group 7. But there are points where hydrogen is going to show its uniqueness. Now, whenever we use the word uniqueness, you're going to find out in what ways it's going to be similar or dissimilar to the two elements that we are comparing it with right now. Now, take a look at the hydrogen. You'd see you can read can form either a positive or a negative ion, which means it may lose an electron to form a positive ion. It may gain an electron to form a negative ion. And when it gains, it actually achieves the noble gas configuration of nearest noble gas, which is helium. Now, hydrogen is actually showing a dual behavior, forming up as positive and negative ion. If I compare it with fluorine, fluorine tends to form a negative ion. So it's actually a similarity with hydrogen. On the other hand, it can lose one electron to achieve a noble gas arrangement, and that way it forms a positive ion, which is again a similarity with lithium. So you'd notice that for the last point, it is actually similar and different to fluorine, and as well as the same thing without a difference though with lithium. Get the point?
Yes,
Good. If you don't get the point, make sure you follow row by row. The first row gives you 1D, 1 and 2S. The second row gives you D, S and S. The third row gives you all S's except the last one is D. And finally, the last point is actually consisting of a couple of points. So hydrogen, similarity and difference at the same time with chlorine, similarity and differences at the same time with lithium. So this kind of structure is possible, hence the unique position. Make sense?
yes, yes.
All right, great. So just a sec